Lula Wang, and I'm a 10th grader. This year, I created an anti-tumor medication for pancreatic cancer. Currently, the pancreatic cancer is the second leading cause of death worldwide, with a 5-year survival rate of less than 10%. Currently, doxorubicin, or DOX, is the leading chemotherapy treatment for pancreatic cancer. However, the issue is that its availability and efficiency is extremely low due to its high toxicity and poor selectivity, causing off-target side effects such as nerve damage, heart failure, and even secondary cancers such as leukemia. Therefore, I engineered a novel nanoparticle system that was shown to overcome all three of these issues. It contains three main functions. Firstly, it has the addition of MEC1, which are the blue antibodies outside of the nanoparticle, which are able to provide specificity to only cancer cells, and therefore avoiding any side effects of targeting healthy cells. Secondly, it used siRNA PDL1, which are able to restore the immune response to prevent tumor recurrence and chemotherapy resistance, which is commonly associated with current medications. And finally, it released doxorubicin once inside the tumor, which allowed to trigger apoptosis for destruction of the tumor. After constructing my nanoparticle, I then took images using SEM and dynamic light scattering, which showed consistent increase of my nanoparticle size. Finally, I then needed to test each separate component of my nanoparticle. Therefore, I conducted my own designs where I reconfigured an ELISA assay using FTIR, and after adding my therapeutic to the bottom of the well shown in the top right, I then used FTIR spectroscopy, which showed that my nanoparticle was in fact bound to MEC1, which is a protein that is overexpressed on pancreatic cancer cells, and therefore proved that my therapeutic was able to target cancer cells and not healthy cells. Finally, I conducted an experiment where I constructed artificial cancer cells versus artificial healthy cells using their corresponding lipid membrane composition. As you can see, after I added my therapeutic, for the membranes of the healthy cells, after 300 seconds, they remained intact. However, at 150 seconds, the membranes of the cancer cells were shown to be disrupted, and at 300 seconds, they were intermixed entirely, showing successful function and specificity of my therapeutic. To summarize, I have constructed a novel chemoimmunotherapy, which is able to overcome all of the current barriers in pancreatic cancer treatment, and it has been shown by an HPLC analysis to increase current drug delivery rates, which are around 40%, all the way to 95%, therefore minimizing the current toxicity that's shown in chemotherapy treatments. In the future, I plan to apply my engineered nanoparticle system to many other cancers as well, such as breast cancer and lung cancer, with the addition of specific targeting mechanisms to their overexpressed proteins as well, in the hopes of providing more cost-effective and efficient targeting mechanisms for chemotherapy treatment worldwide. Thank you for listening. I'd be happy to answer any questions.
You've accomplished so much. So what was your biggest challenge in your research?
Yeah, so I would say one of my biggest challenges is that because I worked in a high school, I didn't have access to living pancreatic cancer cells. So I needed to devise a method that would be able to test each separate component of my therapeutic. And as you can see through the reconfigured ELISA and the artificial cancer and healthy cells, I was able to create my own methods without using living pancreatic cancer cells that were able to mimic the properties of actual pancreatic tumors and therefore show the successful functioning of my therapeutic.
So it sounds like from your answer you did complete most of this out of the high school. Can you explain a little bit about the simulation, like what program it was and what went into that?
Yeah, of course. So for the simulation, which I'm assuming is the artificial cancer and healthy cells, yeah, so what I did was I looked at previous literature and found what the lipid membrane compositions are for healthy cells and actual pancreatic cancer cells. And I realized that those compositions for healthy cells were 100% DOPC, which is a lipid, but for cancer cells, the composition is 70% DOPC, 10% DOPE, and 20% DOPS. So I constructed those corresponding lipid compositions, and what I did was I actually created this chamber that was able to blow bubbles that were essentially GUVs, which were basically bubbles, and the outside of them had those lipid membrane compositions after I dried them. So after putting water in, I used AC voltage to make those bubbles and were GUVs. And then once I did that, I looked under fluorescent microscopy because I added rhodamine, which was able to make it more visible for under the fluorescent microscopy. And then I was able to take those images shown over there using that microscopy, which then were able to indicate the membranes showing that they were dissoluting or dissolving at some point. And then they were completely intermixed at 300 seconds. So that's how I conducted that experiment, and I added my therapeutic to prove each of those steps.
Was there anything surprising that you came across? Maybe something you had to overcome, a challenge that surprised you, that you weren't expecting?
Yeah, of course. So I think one of the challenges or one of the results that I wasn't expecting was definitely the HPLC analysis. Because as I stated before, current chemotherapy treatments, they have delivery rates of around 30 to 50%. And the issue with that is that most of it is getting lost either by targeting healthy cells, which causes all of these other side effects. But it's also a problem because it means that not all of the therapeutic is actually getting delivered to the tumor. So what pharmaceutical companies end up doing is actually increasing your dosage so that you are getting that 100% release rate. And the problem with that is that it causes more toxicity, more side effects, which is something that we don't want happening. And so what I realized after conducting an HPLC study, which what it does essentially is I use serial dilutions to show what you're actually getting out of the therapeutic once it's in the tumor microenvironment and once it's in the tumor. And when I compared that to what was originally in my therapeutic when you first take it, it had a 95% release efficiency, which is much, much higher and almost 100% improvement from current medications. And I thought that result was definitely surprising and something that I wasn't expecting from my research. But it was great to know that that was the case, and that was what I was hoping to achieve through all of the different coatings and layers that I composed in my therapeutic.
Unless somebody else has a pressing question, we have time for this session. Yeah?
Hello, thank you for your presentation. Regarding the small interfering RNA, how did you figure out which sequence or what to pick for that? Like, what was your process for that?
Yeah, of course. So one of the main checkpoint inhibitors or proteins overexpressed specifically on pancreatic cancer cells is something called programmed death ligand 1 or PDL1. And what it does is that it binds to PD1, which is a receptor on T cells, and that therefore prevents immune response, which makes it so that tumors over time develop chemotherapy resistance or tumor recurrence where you can get that tumor later on. So what I wanted to do was find a way to target that PDL1 gene so that I could suppress its function. And so what I found out was that siRNA PDL1 are able to bind to the mRNA that codes for PDL1. And when they bind to it, it degrades that siRNA or the mRNA over time, meaning that the PDL1 expression disappears. And so I thought it would be a great idea to incorporate siRNA PDL1 into my therapeutic so that once it's in the tumor, it can bind to the mRNA, prevent the production of PDL1, and then therefore there's nothing stopping the T cells from functioning, specifically CD8 plus T cells, and then that makes them able to, again, restore immune response, making it so that the body is able to recognize these tumors in the future and prevent resistance that can be developed over time.
Excellent. Thank you so much.